So this is joint work with Sharon Schramm, and it's about invariant inference, a set of techniques for proving the safety of transition systems. So suppose we have, for example, a system over, say, n+1 propositional variables representing a number in binary, which starts from 0, and in each step incremented by 2. This defines the reachable states of the system. And now we want to prove that no reachable state is a bad state, and here being bad is being this number 10001 or 2 to the n+1. So we want to prove that if we start from 0 and iteratively add 2, we can't get to this bad number. To do this, we want to find an inductive invariant, which is a set of states that contains the initial states, doesn't contain any of the bad states, and it's closed under transitions of the system. There's no transition from inside the invariant to outside the invariant. For example, the property that the number is not the bad number, of course, holds, but it's not an inductive invariant because there is a transition from a state inside the invariant, from 0, 1, 1, 1, 1, 1, to a state outside the invariant, to the bad number. So there is such a transition of the system. So this is not an inductive invariant, but we can strengthen it to say that the least significant bit is 0, that the number is always even, and this is an inductive invariant. It holds for the initial states, it doesn't hold for the bad state, and it's closed under transitions of the system. If you start from an even number and add 2, you also end up with an even number, a fact you may have heard somewhere else before today. So once we have such an inductive invariant, it contains the reachable states of the system, separating them from the bad states, establishing the safety of the system. So what we want to do in invariant inference is to automatically find such inductive invariants, resulting in fully automatic safety verification. A lively research direction in the last decade or so compares and contrasts invariant inference with another area of computer science, that of learning theory, and specifically the theory of learning concepts or classifiers, exactly using queries in the style of I'm doing, where by interaction with a teacher, we want to separate the good points from the bad points, positive examples from negative examples. And this is somewhat similar to what happens in invariant inference when we want to separate the reachable states from the set of bad states, except that invariants are defined in terms of reachability, which is a new and interesting concept. So what many works have been doing is taking the very rich theory and algorithms that have been developed in learning theory and adapt them to invariant inference, resulting in theory and algorithms for invariant inference. In this work, we take a specific piece of work called the monotone theory by Bshouty, which was very influential in exact concept learning. We adapt it to invariant inference, and the results are algorithms with provable complexity guarantees, both in abstract interpretation and in the context of interpolation-based invariant inference. And again, algorithms for which we have formal guarantees about the number of SAT queries they need to perform before they converge to an invariant. So our contributions parallel the technical achievements of the original monotone theory. So what Bshouty did, he defined an operator called the monotonization of a formula psi with respect to a state or a valuation sigma. So everything I'm going to do is in propositional logic. He defined this monotonization operator and provided an efficient way of learning the monotonization of a formula. Using this, he obtained an efficient algorithm for learning formulas of very rich and complex syntactic forms. So our first contribution is we developed an algorithm for finding monotonizations that's appropriate for invariant inference, and use this algorithm to obtain an efficient invariant inference algorithm for inferring invariants of rich and complex syntactic forms in the context of interpolation-based invariant inference. However, the way we obtain the learning algorithm from the algorithm for monotonizations is inherently different from the way Bshouty did this, and this is because invariant inference and learning are two different settings with different limitations and capabilities. So we could do things that Bshouty couldn't, and vice versa. So we needed to do some new things to be able to obtain this invariant inference algorithm. So this is, and the reason is that if you're familiar with exact concept learning, then there's a teacher that answers membership and equivalence queries, and in previous work we have shown that this is impossible to do in general in invariant inference, and there's no way to directly translate algorithms from exact concept learning to invariant inference, so we had to work harder than that. So this is one contribution. And the second contribution is an efficient algorithm for performing abstract interpretation in a domain based on the monotone theory, that has been used to study in previous work overapproximation in property-directed reachability. And both these algorithms have provable complexity guarantees for the number of SAT calls they require before they converge to an inductive invariant. So this is what we're going to do today. Actually, both these algorithms rely not on just an efficient way of computing monotonizations, but on a super efficient way of computing monotonizations, one whose complexity supersedes the complexity of Bshouty's original algorithm. And this, again, is possible because we're in the setting of invariant inference and not of learning, so we could use, we have the full power of the SAT solver at our hand. So I'm going to spend most of my time talking about this part and say a few words about abstract interpretation towards the end of the talk. So our goal now is to efficiently infer invariants that have rich and complex syntactic forms beyond monotone invariants. So I'm going to show you the algorithm with the best complexity guarantees we previously had. Then I'm going to show you our algorithm and how it improves on this complexity analysis. So this algorithm of model-based interpolation, originally by Chocolate et al., works like this. So at each point in the algorithm, we have some candidate invariant. And unless we are done, there's a counterexample to induction, a state inside the invariant that can go to a state outside the invariant. So what we want to do is to exclude this set from this counterexample from the candidate. However, we don't want to exclude a single state at a time. This would converge very slowly. We want to find a larger set of states to exclude at each point. The way we do this the way model-based interpolation chooses this set of states to exclude is by generalizing from bounded unreachability. So we choose a value k, which is a parameter of the algorithm, and ensure that the counterexample is not reachable in k steps from the set of initial states. If it does, then that means that we have excluded too many states in previous iterations and need to restart the algorithm with a larger k. But suppose that the counterexample is not reachable in k steps. So bounded model checking shows that it's not reachable in k steps. So we want to generalize this and find a larger set of states with the same property, that no state in this set is reachable in k steps. So that when we exclude this set of states from the candidate, we haven't excluded any state that's reachable in k steps. And in the algorithm by Chocolate et al., this set is constructed as a conjunction of literals, a term or a cube, so many terms for the same thing. So we start from the conjunction that captures exactly the counterexample and then drop some of the literals to capture additional states. So for example, if the counterexample is this, 1, 0, 0, 0, 1, then we may take as the set or the interpolant this smaller conjunction, which is satisfied by more states, and then exclude that set from the candidate as long as this would not exclude any states reachable in k steps. So overall, the way Chocolate et al.'s algorithm works, it always infers an invariant in conjunctive normal form as a conjunction of disjunctions of variables and negations of variables, where each conjunct is obtained by finding a counterexample to induction and generalizing it by dropping some of the literals as long as this bounded model checking query is still satisfied, as long as we're not excluding any states that are reachable in k steps. So what can we say about the complexity of this algorithm? So in previous work, we've shown that this algorithm successfully finds an inductive invariant in a number of queries that's bounded by the number of variables squared times the CNF size of a target invariant I star, where the CNF size of a formula is the smallest number of clauses required for representing it in conjunctive normal form. So the algorithm finds an invariant in this many queries whenever the invariant satisfies two conditions. One is that it is k-fenced, and one is that it is monotone. So being k-fenced, or the fence condition, this is a condition about the interplay between the invariant and reachability. And it says that if we think about the state space of the system as vertices of the Boolean hypercube, then if, for example, this is the invariant, then we're thinking about the boundary of the invariant, which are the states that are just inside the invariant. If you flip just one bit in any of these states, you can get to a state outside the invariant. So the set of states that are Hamming distance 1 from outside the invariant. So this is the boundary of the invariant, and what the fence condition requires is that all the states in the boundary are reachable in k steps. So in a sense, bounded model checking, if this condition is satisfied, then through bounded model checking, we can at least partially detect the sort of edges of our invariant. So this is the condition we require about reachability. And it's quite versatile, allows for some very interesting cases of invariance. Also, in every system, in every safe system, there's at least one invariant that satisfies this fence condition with a large enough k. So this fence condition is cool. The challenge is the fact that we also require another condition, that the target invariant be monotone. And being monotone, it means that we can write the formula without using negations. So, for example, this formula is a monotone formula because all the variables appear unnegated, being equals 1 or being, we require things to be true, so no negations. However, this formula is not monotone because there is this variable x0 that appears negated. So, we require it to be false. So this is not a monotone formula. The problem is that we want to be able to efficiently infer invariants that are also non-monotone. For a slightly more interesting example, if we, for example, want to say that at least two variables are 0 and at the same time always at least two variables are 1, then this is this formula is not monotone. We require some variables to be 0, to be false, and it's really inherently not monotone. There's no way to rename the variables so that this formula becomes monotone. But we still want to be able to infer such invariants efficiently. So our goal is to devise an invariant inference algorithm that can provably infer invariants with complex syntactic forms that are beyond monotone invariants. This is what we do, and our algorithm, which we call CDNF Interpolation, it's an invariant inference algorithm that's inspired by model-based interpolation and Bshouty's CDNF learning algorithm. And it can be shown, or we show that it successfully infers an invariant in a number of bounded model checking queries bounded by the number of variables squared times the CNF size of the target invariant I star, this time times the DNF size of the same target invariant I, where the DNF size is the smallest number of terms required to represent the formula in disjunctive normal form. As long as the target invariant I star satisfies the fence condition. But notice that there is no condition here about I star being monotone or close to monotone or anything of this sort. Under the same condition about reachability as before, we are able to obtain efficient invariant inference for the target invariant I star, as long as it has both polynomial size CNF and DNF representations. So for example, the same formula from before saying that at least two variables are 0 and at least two variables are 1, if we write it this way as a disjunction, of saying we choose 4 bits that satisfy 4 variables that satisfy what we need, then this shows that this target invariant has DNF size of polynomial in the number of variables. We can also express the same formula in an equivalent form in CNF, saying that for every variable we choose, there's always another variable that is 0 and another variable that is 1. This is exactly equivalent, and it shows that the CNF size of the target invariant is also a polynomial in the number of variables, which means that our CDNF interpolation algorithm can efficiently infer this inductive invariant, again, as long as it satisfies the fence condition. The class of formulas, or the class of invariants that have both short CNF and DNF representations is very rich, and for example, contains all the formulas that can be expressed as Boolean decision trees of polynomial size. The overall structure of the algorithm is exactly the same as the model-based interpolation algorithm from before. At each point, we have a candidate invariant. We find a counterexample to induction that we want to exclude, but this time we generalize not by finding some conjunction, but by taking the monotonization of the set of k reachable states. So I think this is time I said what the monotonization operator of Bshouty really is. So our starting point is monotone formulas, as the monotone theory name may suggest. So if we think about it slightly more carefully, or more formally, a formula is monotone if and only if it can be written in disjunctive normal form, as disjunctions of conjunctions of variables and negations of variables without negation. So all the variables appear only positively. And the intuition for the name monotone is that such formulas are closed under flipping variables to true. If you start from a state that satisfies the formula and you flip a variable to true, then the resulting state also satisfies the formula. So the first step in the monotone theory is to generalize monotone formulas to sigma monotone formulas, where sigma is some state or evaluation. So a formula psi is sigma monotone if it has a DNF representation where all the variables appear in polarity opposite to how they appear in sigma. So for example, if we take sigma to be 0, 0, 0, 0, then the first formula is 0, 0, 0 monotone because all the variables appear in polarity opposite to how they appear in sigma. However, the second formula is not 0, 0, 0 monotone because this variable x0 appears in polarity the same as it appears in sigma. So we can see that being 0, 0, 0 monotone coincides with the previous definition of monotonicity. Things get interesting when we mix it up a little and choose a different value for sigma. So if we take, for example, the valuation 0, 0, 1, 0, then the first formula now is not 0, 0, 1, 0 monotone because the variable x0 appears in polarity the same as it appears in sigma. And the second formula is 0, 0, 1, 0 monotone because all the variables appear in polarity opposite to how they appear in sigma. So these are sigma monotone formulas. And the intuition here is that such formulas are closed under going further away from sigma. So if we have a state that satisfies the formula and we flip a variable to disagree with sigma, then the resulting state also satisfies the formula. So the monotonization of the formula is the least overapproximation as a sigma monotone formula. So the monotonization of a formula psi with respect to evaluation or state sigma is the least formula with respect to implication or inclusion that is sigma monotone and contains the original formula. So for example, if we take the formula saying that all the variables are 0 and take the monotonization with respect to 1, 0, 0, 0, 1, then this is the monotonization. It's a 1, 0, 0, 1 monotone formula, and it's the least 1, 0, 0, 1 monotone formula that contains the original one. So one thing to observe here is that one way to obtain the monotonization from the original formula is by dropping all the variables that make the original formula non-sigma monotone. So here we drop all the literals that agree with the corresponding value in sigma. This holds for a conjunction, and it also holds for disjunctions of conjunctions. So Bshouty shows that a DNF representation of the monotonization can be obtained from a DNF representation of the original formula by dropping the literals that agree with that appear in the same polarity as they appear in sigma. The way Bshouty used monotonizations for learning is that he represented a formula psi as a conjunction of monotonizations of the same formula with respect to different valuations. And what we're going to do in our invariant inference algorithm is the same. We're going to represent to infer the invariant as a conjunction of monotonizations of the invariant with respect to different valuations. The valuations are going to be our counterexamples. And we're going to do that without actually knowing the target invariant until we find it. So in our CDNF interpolation algorithm, generalization always returns the monotonization of the set of k-reachable states. And what we show is that under the fence condition, the monotonization of the set of k-reachable states is exactly the same as the monotonization of the target invariant. So we can find the set of k-reachable states. We don't know the invariant, but under the fence condition, it turns out that the monotonizations are always the same, which means that our candidate invariant is always taken to be a conjunction of monotonizations of the invariant, again, without actually knowing the invariant, thanks to the fence condition. And it's possible to show that the number of counterexamples required for this process to actually converge to the inductive invariant, we have taken enough monotonizations in the conjunction, is bounded by the CNF size of the target invariant. It's really important for the complexity of the algorithm to be able to find the monotonization efficiently, and our monotonization algorithm runs in complexity that a number of subqueries bounded by the number of variables squared times the DNF size of the output of the monotonization. This is as opposed to Bshouty's work, where this was number of variables squared times the DNF size of the input formula. And it's really important in our application because what happens here is that we take the monotonization of the k-reachable states, which may be a really complex formula to represent. However, because the monotonization is exactly the same as the monotonization of the invariant, then we know that the DNF size of them are exactly the same. And we can show, as Bshouty does, that the DNF size of the monotonization is always less than or equal to the DNF size of the original formula. So when we perform monotonization through our algorithm and improve complexity of our algorithm, it runs in time bounded by the DNF size of the target invariant and not the DNF size of the set of k-reachable states. Just to say again that this algorithm is inspired by Bshouty's learning algorithm, but differs from it significantly. All the details are in the paper, and are due to the fact that the defense condition gives us some information about the target invariant, but not full information about the invariant. So some of the things that Bshouty does, we can't. So we do other things like taking the monotonizations of the k-reachable states, a concept that doesn't exist in the original learning application. Okay, so just a few quick words about abstract interpretation. So we can think about the logical abstract domain that consists of all the sigma monotone formulas when we choose a specific sigma. We call it the monotone span of sigma. And then in a Galois connection between this logical abstract domain and the concrete domain of sets of states, then it turns out that the abstraction function is exactly the monotonization operator of Bshouty. And we were interested in this abstract domain because we've previously used to study overapproximation in property-directed reachability through this domain. So we can show that property-directed reachability overapproximates at least as much as abstract interpretation in this abstract domain. So what we did in this work is find a way to efficiently implement the abstract fixed point computation in this abstract domain. So it runs in a number of subqueries bounded by the number of variables squared times zeta squared, where zeta is an obscure Greek letter that's here defined in terms of the DNF size of the monotonization of the transition relation formula. And the fact that it's the DNF size is really important because it's an indicator of overapproximation. We've previously shown that the number of iterations in the fixed point calculation in the concrete domain is bounded by the DNF size of the transition relation formula, and the number of iterations in the fixed point computation in the abstract domain, in this specific abstract domain, is bounded by the DNF size of the monotonization of the transition relation formula. So the fact that when the DNF size of the monotonization is much, much less than the DNF size of the original transition relation, that's a good sign. It means that it might be a good idea to use the abstract domain. So it was important for us to obtain an overall complexity bound for abstract interpretation in this domain using the same quantity. And this is thanks to our improved complexity of our monotonization algorithm compared to Bshouty's original algorithm. We also have an extension of this result to the reduced Cartesian product of monotone span domains, where the similarity to property-directed reachability really comes up, and all the details about abstract interpretation in these domains appear in the paper. So overall, I talked about how based on and inspired by and through developments in the monotone theory, originally work in exact concept learning by Bshouty, we have obtained two algorithms with efficient complexity guarantees, one for inferring invariants of rich and complex syntactic forms in the context of interpolation-based invariant inference, and the other for abstract interpretation in a domain that has previously been used for studying property-directed reachability. Thank you.
Other question? Okay.
So this is very interesting, but I'm curious. So this is a different way of doing generalization in both interpolation and PDR/IC3, and I'm curious if that has an empirical effect on actual implementations in practice. Like, does this produce better or worse invariants in practice? Do you have any idea?
So I hope it does. I don't have any results about it. There are several interesting technical challenges on the way there, but I think it's a really interesting direction. Not even to, if these algorithms work well, then great, but even incorporating some of the ideas here to existing interpolation and property-directed reachability algorithms, I think that's a super interesting direction.
Thanks.
Other questions?
Hi. Do you think any of this would work for infinite state systems as well, at least in principle?
I'd love to know too. It's interesting because there's also not much work already in learning theory about logics beyond propositional. There's a few works about restricted fragments of first-order logic, but there's no monotone theory for other logics. So it's a really interesting direction.
Other questions? I have one. So monotonization is kind of, you show it's an abstraction inside your framework. I wonder if absent interpretation can learn something from using monotone functions, and whether the distance between formulae in a quasi-metric space can help to have some sort of measure of the precision inside the abstract domain. Do you think it's possible?
That's a deep question.
I don't know. It was fun.
So you're thinking about the distance?
Yeah, I mean, try to measure. I mean, you're working in a domain of Boolean functions.
Right.
And that's your abstract domain.
Right.
And but you can probably design distances between logical formulae. And I wonder if the use of Boolean functions in particular may help you in having a kind of metric of the precision of the analysis when it runs on the monotone case. I don't know. I mean, you are the first that probably use from my side this theory in abstract interpretation.
So I don't know. It sounds interesting. I have some like very vague thoughts now, but like in a very vague way. So maybe thinking about conjunctions of closure properties, and as happens in the monotone theory, like the monotonization is a sort of closure, but then taking the conjunctions in a way that has a lot of structure. It's not an arbitrary product of domains. There's something we can say about something to think about.
Okay, thank you. Okay, let's thank the speaker again.